Alright, welcome back to the AI Research Roundup. I am your host, Alex. Today we're diving into a paper that's been trending called Vision Transformers Don't Need Trained Registers. So the researchers looked at a known issue in vision transformers where certain parts of the input get overemphasized, creating what are called high norm tokens. These high norm tokens can make the model's attention messy. The old fix required retraining the model with special register tokens to soak up this noise. But this paper proposes a clever, training-free solution by identifying the specific neurons causing the problem and simply adding a new, untrained token during testing to handle their output. It's a really neat idea, and if you want to try this technique out for yourself, the authors have released the official code in PyTorch. The repository looks super useful. It comes with ready-to-use models on Hugging Face that already have these test time registers integrated. You'll also find example notebooks for popular vision transformers like Dino vs. 2 and OpenClip, which makes it easy to see this method in action. And this first figure really shows the whole story visually. For the OpenClip and Dino vs. 2 models, you can see the input image, like the eagle, and then the original attention map next to it. An attention map is basically a heat map showing what part of the image the model is focusing on. In the original maps, you see these bright scattered spots. Those are the noisy high norm tokens we talked about. To prove they understood the cause, the researchers then show they can shift these spots into specific shapes, like a smiley face. Finally, with their test time register added, the attention is cleanly focused on the actual subject, making the model's focus much clearer. So how did they even find these problem spots? Well, this next figure gets to the heart of their discovery. It shows what's happening at the level of individual neurons. On the left, for a normal image patch, you see a nice, symmetric distribution of neuron activations. Pretty standard stuff. But on the right, for one of those outlier patches, the story is completely different. Most neurons are basically silent, but a tiny handful, less than 10 in fact, are firing with extremely high values. This discovery of a small set of what they call register neurons is the key insight that makes their whole training-free approach possible. Okay, so building on that discovery of the register neurons, these charts really pinpoint the cause and effect. On the left, we're looking at signal strength, or norm, across the model's layers. You can see it's low until layer 6, where right after a processing block called a multi-layer perceptron, or MLP, it just skyrockets. A multi-layer perceptron is a part of the network that helps process features. Then, the chart on the right shows the immediate consequence. In the very next layer, the attention score spikes, showing the model is now distracted by that noise. It's a clear chain reaction. And this next visualization really drives that point home. We start with an input image and a map of its patch norms, which again is just a heat map of signal strength, and we can see the bright yellow outlier spots. Now the really cool part, the other panels show the activation maps for individual register neurons from layer 6. You can see that a single one of these neurons lights up in the exact same locations as all the outlier spots. This is the key evidence. It proves it's the same small group of neurons creating this global noisy pattern. And so, this figure really shows the payoff of their discovery. We're looking at attention maps from the Dino vs. 2 model again. The original column is what we've seen before. The attention is basically just a single noisy spot, not focused on the subject at all. But in the middle column, with their test time register added, the attention map now cleanly highlights the dog and the pizza. And the most convincing part is comparing it to the last column. That's from a model fully retrained with registers, and the quality is almost identical. This is the key evidence that their training-free fix works just as well. So, we've seen the visual proof that the attention maps get cleaner, but does this fix actually hurt performance? Well, this table answers that with some hard numbers. What we're looking at here are results from a test called linear probing, which is a standard way to check how well a model's internal features can be used for a task like classification. The key takeaway is in that bottom row. The performance of their test time register, across all 3 datasets, is almost identical to a model with trained registers, and it perfectly matches the original outlier token. This is strong evidence that their method successfully isolates that noisy global information without damaging the model's overall capability. Alright, so this next figure demonstrates the precise control they have over this whole process. It's not just about cleaning up the maps. They can actually move the outlier wherever they want. On the left, they've picked a random patch from the image. The yellow distribution shows that this specific patch now has that extremely high norm, or signal strength we saw earlier. Meanwhile, the blue distribution shows every other patch in the image remains normal. Then, the graph on the right shows the consequence. The model's attention is now completely focused on that same random patch. This proves they have direct, causal control. What this all demonstrates is a really elegant piece of detective work. The researchers took what seemed like a messy flaw in vision transformers, this outlier token, and showed it's actually a predictable, controllable mechanism for storing global image information. Their training-free fix not only cleans up attention maps on the fly, but gives us a deeper understanding of how these models see the world. Thanks for tuning in to the AI Research Roundup. I'm your host, Alex.